All right, so why don't we take a look at this test review that I handed out there. Let's see, why don't we start with what to be looking for on this test. So this is Monday. So chapter 9, we did the flow rate stuff, Q equals VA. We also did it with changing pipe diameters. So I'm sure there'll be something like that on the chart, or excuse me, on the test. Now keep in mind, you can use the chart if for a lot of different situations there. What you have on that chart on page 108, which I'll give you a copy of for the test, is you have flow rates in gallons per minute in different pipe sizes. So that will get you, for the standard pipe sizes and flows in gallons per minute, you can find the velocity right on that chart if you need it. But also I might give you one where the pipe size isn't on that chart. So you should be ready to do kind of Q equals VA in some fashion. All right, the next thing there is the idea of energy and water. That's chapter 10. That also works its way into chapter 11 because that's really why we want to do this. We look at elevation head, pressure head, velocity head, and head loss, and we put them on a chart. Doing that's called Bernoulli's equation. So we covered that in chapter 10, and we also did it in chapter 11. The difference was in chapter 10, I said the head loss is such and such, whereas in chapter 11, you found the head loss. Okay. So that was the difference. The other thing we covered in chapter 10 was hydraulic grade line too. So you should know how to do that. All right, now in chapter 11, we got into head loss. We want to know the basics of the theory, what does and does not cause head loss, and know the difference between laminar and turbulent flow. The whole Darcy-Weisbach stuff, which I think was problem 11.1, that will not be on the test, okay? So you don't need to worry about that. That's that complicated way of calculating head loss.
Is it laminar and turbulent?
Yeah, laminar flow is smooth flow. So laminar is like if you got a nice smooth pipe and there's no turbulence, the water would just go in straight lines. Okay, that's called laminar. The way to remember that is you think of the word laminate, put plywood sheets together, they're all thin and parallel, just like the water would flow in thin parallel lines. That's how I would remember that. Turbulent, so
Something like a rough pipe?
yeah, turbulent is like in a stream or a rough pipe or something. Turbulent is actually the norm. I mean, that's normally how water flows. It does, it goes all over the place, okay? So that's turbulent. And that is the norm for how water flows. Okay, okay, chapter 11, we did the Hazen-Williams, which is the chart, the head loss chart. And of course, I'll give you a copy of that too when you take the test. And that's on page 108. And you should be able to use that for C equal to 100, but also C not equal to 100, where you use the equivalent flow. All right, so you want to be able to do both of those. Okay, so I'm sure I'll give you some head loss energy kind of problems where you use a chart and you find head loss. So you should be prepared to do that and to calculate pressures and that sort of thing using the chart. Okay. And then the last thing is the minor losses, which are head losses in fittings. And to do that, you find an equivalent length of the fitting. So basically, you take the fitting and convert it into a length of pipe, and then you find the head loss for the length of pipe. All right, now I've got some example problems. These are from an old test. I mean, don't now look over all of your homework to study for this thing. There are some things that I've mentioned that aren't on these example questions. So, don't make too much of them, but all the same, look them over and understand them. They're pretty typical types of problems that I might ask. Okay, so number one there, how would the factors below affect head loss? If you have rougher pipe, of course, you're going to get higher head loss, right? I mean, that's pretty straightforward. However, we did cover that the pressure doesn't affect the head loss. So head loss is independent of pressure. All right, now the next one is a Q equals VA problem there. And that one, you're not going to have, 15-inch pipe is not on the chart on page 108, nor is 5-inch pipe. So you have to do this one by hand. And we want to find the velocity out of the pipe. All right, so what you want to do here is you first realize I can't use the chart on page 108 to do this. The second thing I notice is I'm putting low velocity water through a big pipe, then I'm necking it down. That's basically like a nozzle. So I would expect the velocity to go up on that one, okay? So then what you want to do is calculate the areas. And normally I do that first thing, okay? So if I've got 15-inch pipe, I've got the radius of the pipe is 15 over 2. So that would be 7.5 inches. And here the radius is 5 over 2. And that's 2.5 inches. Okay. So once you've got that, then you can find the areas, because that's what you're going to need. When you have this type of problem, what you're doing is you're doing Q equals VA is what you're doing on this. So you're going to want to, get those areas. Now you'll notice that the velocity is in feet per second. So you're going to want an area in square feet. So you want to get the radii converted into feet. So the way you do that is you divide them by 12. Okay, so that first one is 0.625 feet. And the other one will be 2.5 inches over 12. So the other radius then will be 0.2083 feet. Okay, so we got the two radii now in feet, which is how you want to have them. And once you have that, you can find the area. And that would be pi times 0.625 feet squared. And this would be pi times 0.203 feet squared. Excuse me, 2083 feet squared. All right, so you can get the area of each side of the pipe there. The first one comes out to be 1.23 square feet. And the other one comes out to be 0.136 square feet. All right, so a little bit of work there, but you want to find the area of both sides in square feet too. That's kind of an important part of that. So once you've got that, then you want to go Q equals VA. So to find the flow rate, you want to take the velocity, and the velocity there given is 1.2 feet per second, and you multiply it by the area, 1.23 square feet. So what you get then is the area, or excuse me, the flow rate going through the whole system, and that's 1.47 cubic feet per second. So every second there's 1.47 cubic feet coming into that system, and we would assume that's what's coming out also. Okay? So if Q is V over A, now we've got Q, we want to find the velocity. We can do that algebraically. The velocity is Q over A. So now we can find the velocity by taking the flow rate, 1.47 cubic feet per second, and we divide it by the area out, 0.136 square feet. And if you do that, you'll come up with the velocity out, and it's 10.8 feet per second. So that's the standard way to work through that. So do we have any questions on that? Now, there's also a shortcut way to do this. Now, it's not on a formula sheet anywhere that I know, but there's a way to do it, because what you're doing, you're taking this velocity, 1.2, and you're multiplying it by pi times the radius coming in squared, and dividing it by the area out, which is pi times the radius out squared. So what you can do is take 1.2 feet per second, and you can cancel those pi's. See, they both cancel out. And what you can do is look at the ratio of the radius in, which would be 7.5 inches, divided by the radius out, 2.5 inches. And being as you're doing a proportion there, those units cancel out, so you don't even have to convert into feet if you don't want. You can just, as long as the units on that ratio are the same, you don't have to worry about them, because they'll just cancel, and you're going to square that. So that's 1.2 feet per second times the ratio is 3. It's unitless, and you square that. So 3 squared is 9, and 9 times 1.2 is 10.8. So that's the quick way to do that if you want. But you do have to remember that, because I've not seen that on formula sheets anywhere. So, do we have any questions on that? So that's the first one. This is that test review. Yeah, you got that one.
I'm sure I got it.
Okay, have a look if you don't. All right. So that's the first one.
Actually, I think you
All right. All right, now the second one is a pretty standard kind of chart kind of problem, okay? And what the deal is you apparently have pressure gauges on this thing. We've got the pressure here is 50 psi, and we want to find the pressure here. Okay, 200 gallons per minute, 4-inch pipe, C100. All right, so this is one of those where you got to go to the chart. You got C100, so that's pretty straightforward to do. You go to the chart on page 108, and I'll give you a copy of that. And then you can find the head loss, all right? I just want to pull up a copy of the chart so we can see it here. There we go. All right, so what we've got on this one is we've got 4-inch pipe, 200 gallons per minute. So you just go over to the 4-inch pipe column and look at 200 gallons per minute. There it is. So it looks like 4.38. That's on page 108. Okay. So 200 gallons per minute, 4-inch pipe. 4.38. Now, once we've got that, then what we want to do is we want to get that filled in, okay, on the for the head loss. So we got 4.38 feet per 100 feet. And then what we've got 945 feet. So if we multiply that by 9.45, we'll get the head loss that occurs in that run of pipe. And that's just based on the head loss per foot, or excuse me, head loss per 100 feet times the length of the pipe in 100-foot lengths. So 4.38 times 9.45. It's 41.39. And that's feet. Okay. So we're doing all right with that? All right, so now we can build a chart. That's how I like to do these. So we've got point A, and we've got point B, and we've got elevation, pressure head, velocity head, and the total. And then we've got the head loss in between. I think we're ignoring velocity head on this, which is commonly done. And then we're going to cross head loss off the list. All right, now what we've got there is we've got 50 psi at A. So if we take that 50 psi, we can convert it into feet. Okay, there's 2.31 feet per psi. So that will become 115.5 feet. So that's the elevation, excuse me, the pressure head there at A. So what we got there, we got 135 feet of elevation, got 115.5 feet of pressure head. So that's going to be 250.5 feet of energy that we have. And then we can take away the loss, which is the head loss, and that's minus 41.39. So if you take 250.5 and take away the 41.39, you get 209.11 feet. So that's the energy you've got to work with at B. Okay, now at B, so we good with that? Okay, at B we've got an elevation of 176. Okay, that's given. So we got 209.11, take away 176, and what you end up with is 33.11 feet. That's the pressure head at B. So if you've got 33.11 feet of pressure head, we know that there's 0.433 psi per foot. We can get that converted into pressure, and that's 14.3 psi. So do we got any questions on that one? Okay. So that's one of those chart problems. I'm sure you'll see something like that. So just get that one kind of worked out. Now remember there, when you're given a pressure to start with, 50 psi at A. You can multiply that by 2.31 and convert it into feet of energy. That's the pressure head. Okay. The total energy then is 250.5. That's at A. The head loss then is, so what we do then to get that pressure head is you multiply by 2.31. When you get the pressure head at B, that's already in feet. So to get that back into pressure, you multiply by 0.433. So keep those two conversion factors straight, and when you use them. The 2.31 is to go from PSI to feet, and the 0.433 is to go from feet back to PSI. Okay. So, we got any questions on that? Okay. Good. All right. Now the next one is a minor loss problem. And I might have a typo on that thing. I'm not sure. Do you have a 1/4-inch gate valve or half? It should be 1/2 inch, but there might be a 1/4 on some of those handles. Okay, so that's I'm sorry, that's my mistake there. That should have been 1/2 because you don't have a 1/4 on your table to work with. So that's my mistake there. Okay. So that should have been a 1/2 open. All right, so what we got here, we got a 6-inch pipe, which is 1/2 foot. C100, flow rate at 500 gallons per minute. Okay, a 1/2 open gate valve, which is what that should have been. If you look on the table, now I'll give you a copy of this too. This is that minor loss table. That's page 123, I think. Okay, so I'll get you a copy of that. L over D in this case for a 1/2 open gate valve is 180, and that's on that table. Now what D is 0.5. Okay. So what we want to do here is to find the length of the equivalent length of the 1/2 open gate valve, and that's L essentially. So you're going to take L over D times D. So you're going to take 180 times 0.5 feet, and that's going to get you 90 feet, and that's the equivalent length of the 1/2 open gate valve. So once you know what's going on with the gate valve, you can find what's going on with the whole system, because we got the gate valve, but we also have those pipes. So to find L total, we can take 263, that first run of pipe, add the 90 for the gate valve, and add 104 for the second run of pipe. We can add all those up and get the total length. And that comes out to be 457 feet. So the idea on this is that the head loss for this run of pipe, the 1/2 open gate valve, and then the other run of pipe has the same head loss as 457 feet of pipe. That's basically how this method works. All right, now once you've got that, you've got 6-inch pipe with 500 gallons per minute, C100. You want to figure out what's the head loss per 100 on that. So you want to go to the chart on page 108. And you want to go ahead and find that. And what we've got for that, I think we were 6-inch and 500. 3.32, I think. Okay. So that's just off the chart, and that's telling us that every 100 feet of 6-inch pipe with 500 gallons per minute gets you 3.32 feet of head loss. So we got 3.32 feet of head loss per 100 feet, and using that number, we've got 4.57 100 feet lengths. Okay? So if you just multiply those two together, you'll get the total head loss, 15.17 feet. You got any questions on that? All right. All right, now the last one's a little different, okay? Now on the last one, what you want to do is find the head loss, okay? That's how the last one works. So what you've got is you have what's called a required residual pressure at the hydrant, and that's pretty typically 20 psi. So if you convert that into feet, that's 46.2 feet of energy required at the hydrant. 20 psi times 2.31 feet per psi. All right, now the next thing to do then is to kind of look at what's happening on either end of this system. And we've got, we'll call the hydrant, or the reservoir A and the hydrant B. And we're going to look at the head loss that's going to happen in between. We've got elevation, we got pressure head, we got velocity head, which we're going to ignore, and then we got the total. So that's what we got. So the elevation at the hydrant is 367, elevation at the reservoir, I'm sorry. There's no pressure up there because it's open to the atmosphere. We're ignoring velocity head. So what we got in that open reservoir is 367 feet. Okay. Now at B, we're at an elevation of 241. We got a pressure head of 46.2. And we're going to ignore the velocity head. So when we add up what's going on at B, we get 287.2. Okay. So being as we're given a residual pressure at the hydrant, we can work this both ways and figure out what the head loss can be. So we got 367 at the reservoir. We need 287.2 at the hydrant. So if we subtract, we'll get the difference, and that's 79.8 feet. So what that's telling us is we can have up to 79.8 feet of head loss as the water flows. Okay. now, we got 79.8 feet total. But that pipe is 3,572 feet long. That's a long pipe. So that's 35.72 100-foot lengths. So if we divide that out, we're going to take 79.8 total allowable feet of head loss, divide it by the number of 100-foot lengths, we get the allowable head loss per foot. It's 2.23. Okay. Now our goal here is to pick a pipe that will work for this situation. The general idea here is the bigger the pipe, the less the head loss. So what we want to do, we've got a required flow that we need to get to this hydrant of 3,000 gallons per minute. So we're going to go to that table on page 108 and start looking at what we got going on for 3,000 gallons per minute. Okay. So I've got different numbers I could pull up here, 10-inch, 12-inch, 14-inch pipe. We're looking at 3,000 gallons per minute, and we're looking at C100. So for 10-inch, it looks like we got 7.61 feet per 100. For 12-inch, it looks like we got 3.13 feet per 100. And 14-inch, we got 1.48 feet per 100. Okay. I'm just pulling that off the chart. 3,000 gallons per minute for each one of those pipe sizes. Okay. So there's 10, 12, 14. Okay. All right, so once we've got that, now we just got to pick a pipe that'll do the job for us. And let's see what pipe's going to do the job for us. The pipe that's going to do the job for us can't have more than 2.23 feet per 100 feet. So 12 inches, 10 inches is certainly too much. 12 inches a bit much, but 14 inch will work. Okay, so you go with 14 inch pipe. Okay. So we got any, we good with that? That's a bit of a run through some of the basic ideas that'll be on this test. I mean, you want to be able to do Q equals VA. You want to be able to put the table together, find a head loss, and you want to be able to find a minor loss for fittings. Hydraulic grade line would be a good thing to know too. I don't know if that'll be on there or not, but that is something that we touch on.
I think I missed about 1A, the first one.
Yeah.
I know that, I'm guessing that higher pressure and then regular pipe, what are the factors?
Yeah, the factors.
Yeah.
Actually, the pressure doesn't affect it at all.
Nothing?
Yeah, it's odd, but that's the deal. So, but certainly the roughness of the pipe does. So, rougher pipe gets a higher head loss, but higher pressure doesn't seem to make any difference according to the theory. Okay.